Oh, welcome back, folks. I wasn't looking at the clock too carefully. We are ready to get started. Well, we're going to have our very first review for exam one today. The exam, once again, is over these 5 specific units, and it came out to 11 questions. So it'll be about 2 per 3 questions roughly for each unit. I try to select a representative sample on a unit by unit basis. And aside from that, just a couple quick reminders. Don't forget, it's a good idea to start working on your page of notes that you're going to bring to your exam. It'll be of that size. Anything you'd like on it, front or and back, is included. And you can have this printed if you prefer, or just handwritten. Also, don't forget your scientific calculator. It's going to be required for the exam. The testing center does have some backups, but they can in fact run out. So don't forget to bring yours. They may not have one for you. Aside from that, this will be the last page on the exam, like we referred to. And these are the sample exams that you could take a look into after getting caught up on the homework and the quizzes. And by the way, if you get quiz 3 done early, I'll make every effort to have it graded and returned back to you for extra practice on the upcoming exam. But any questions at the moment, folks, about exam one?
Yeah, I guess on our page of notes, you might have mentioned this, but like, what's a good idea to have on that page of notes? Like the formulas for the problems, kind of thing. Like that's my question, I guess. What should we kind of put on there?
And it's going to be pretty much zero restrictions. So that makes it kind of hard to answer, right? It could be anything. Here's what I would do if I was building out my page of notes. I would go through the unit and then on a unit by unit basis, let's open up this one just as a reference one. Look into the problems that are on the sample exam and look for any ideas that you feel like are probably something that is easy to miss that we're really going to need. We started off with just kind of a refresher on fractions. So if I was to scroll down to maybe the first element, that is going to be really critical. Let's see. This one didn't come out the best as a PDF. Sorry about that. But this might be a good one to start including on your notes. Anything indicated as per is referring to division. Of is often meaning multiplication. Squared power 2, cube would be power 3. That might be a good one to put down. Then as we went through the notes on this one, personally, I don't know if I would put down anything too specific so far. But if you feel like there's just one problem that was tricky, like converting 16 weeks to seconds, I have zero restrictions on what you put on your notes. In fact, I won't be collecting them. You're okay with putting down a full example if you'd like. I'm not going to re-ask any of these questions, but you can think of this as a model of how to approach a problem like this one for when you see something related come up in the exam. So I think this one is a tricky one. And if you have a model like this as an example on your notes, that's going to be allowed as well in this class. And then scanning through in this unit so far, I didn't think there was anything too major. Also, keep the notes right here pulled up so that way you're not being too redundant. You're not including anything on here that's already included as that big handout. So I would definitely not put any of this on the notes. Then next, I would go through, let's see if we got anything bigger that pops out at me on a Unit 2B. On Unit 2B, I would say these things are kind of the major thing I was looking for. Exponential laws, exponential notation is going to come up a lot. So I'd probably start writing these down, just maybe collect into one spot. The power rule, AM times A power of N, the division rule, the negative exponent rules are good ones to bring in. Then going down, let's see here. What else do we have? I wouldn't say include that table. That would be a bad idea. Any of this kind of information that we need, I'll include in the write-up of the exam for any strange units. This one's included and the last page of the notes. And so is this table here. And I think that pretty much does it for this unit. Going off to the next one, let's skip this one and go to this one, percentages. A good formula might be just the standard percent equation here, or absolute change versus relative change would be a good one to include on the notes. And so that'd be my major guidance so far. Include just details on computations, definitions, tables that give interesting ideas not already included on the major handout. Any example that you want to put down as a model, just as a refresher, is not a bad idea either. And, aside from that, a next good thing to do is you could go into the textbook. We didn't copy everything in the textbook verbatim into the lecture notes, or else we might as well just use the textbook as the lecture notes. But let's go into it just a minute to fully address that question. Get into the textbook. It takes me a while to get in there. I think I'm just about there now. Click on eText. Click on here again to finally open the textbook. It's like a journey just to get inside here. And there's some pretty nice tables here that you might want to bring in. So let me go to table of contents finally. And I have one table I'm looking into specifically. I think it might be in unit 3B. There we go, unit 3B, putting numbers in perspective. Let's go past the learning goals page. Discussing scientific notation, and anything that has a brief review is possibly good information you want to put on your notes as well. Let me see if I might not be in the right unit I was thinking of for the thing I'm looking into. Yeah, let me move over to 3C. So there's 3A, 3B, 3C finally, uncertainty. And in this unit, we have significant digits defined. Oh, this goes beyond the exam. Sorry. Even though this one's not on the exam, I felt like this was a pretty nice table to have as well. So look for these little boxes that say brief review. It has a lot of great stuff like exponential notation, scientific notation refreshers. And this one, it happens to be on a unit we're not going into on the exam, 3C. We're ending in 3B. Let me double check that. Yeah, 3B. But this is still a pretty great table. Let's actually throw this in our exam review notes. This would be a good thing to have ready to go on the exam as well. So I'm going to drop it in here. These are the notes that we're going to build out for the student-directed questions, like the first one you started us with. Thanks for asking about that. And I'm going to post those notes when we're done with them over here, just on the last element, actually probably above quiz 3. I'll post exam 1 review. But that would be my guidance. Scrub through on a section-by-section basis, look through stuff in the book, and you'll probably find out with a lot of good ideas for things to put in. But does that help with that question there, Zach?
Yeah, that was great, actually. Thank you.
Yep, you bet. So again, it's a pretty wide open set of notes. Look for definitions, theorems, review information like this one we pasted in, and examples you've worked before, old quizzes you worked before, even problems that you see as actual homework problems in the homework system itself. That's all fair game. So another approach is you could go course home. This is more what it might look like, the student home. Entire course to date. Actually, it's showing me, again, not everything. Go to entire course to date to reveal everything. Now, if you found a problem that you just felt was kind of tricky, let's go and see maybe 3B. See what question 7 was. Sometimes the last question feels like the trickiest. It's not always true. If you felt like this was a pretty tricky question, you could click on, say, help me solve this. It'll give you kind of a step-by-step journey on getting through this. You'll get a nice page of notes. It's going to make you do some work on this eventually. But you could give a pretty good wrap-up to what this one is and include this in the notes for your problem on the step-by-step process of solving a problem like this one. So that would be another great idea for building out the notes. Let me see if it's question 4. Let's see, could an average person lift the weight of $100 in dimes? This is kind of an arbitrary question. So again, you can click on get more help. There's no help me solve this one on this one. That's kind of weird, kind of strange. Guess it's because it's just a multiple choice question. This one didn't work out too well for what I thought it would do. How about question 6? Huh. Yeah, some of them don't have as much resources as I would expect, but you can possibly click on a video for something related and build out notes on what's probably like a PowerPoint slide presentation for the video on these kind of questions. Then you'll get a good idea what is the step-by-step process, and you can build that right into your notes as well. So that gives you some ideas to get started. Other questions so far to start us out today on our review? It could be overall concept questions like Zach asked on what should I even put on the notes? That's a great question. Or specific problems as well, I'm happy to take a look into. So any overall questions or specific problems that folks have today to start us out? Okay, at this point, what I'll do is after taking on any review, the open questions from anyone in the class, I'll start building into just an overall arcing review to fill out the review for the day. And what I mentioned before is I'm going to look into this document here. This is the one that has some fresh problems. It's a long section. I think there's about 25 problems altogether. So my goal isn't to try to get from problem 1 to problem 27. We won't make it. I'll pick out just specific problems I feel like is a good representative problem for the unit, which might make a good exam problem itself for that unit. So I'll try to hit all units today. I'll pick 1 or 2 problems from this section here. And if any questions comes up as we're looking into these problems, don't hesitate to just say, hey, can we take a look into problem 3, what I might skip over, for example, or if there's another question that comes up right in the middle that you want to take a look into from any source whatsoever, I'm happy to pause our overall review here and jump into your question. So we're going to attempt the possible of taking what is 27 questions and try to distill it down in the remaining time we have. So I'd say a good question to start off is, let's go with question number 1. Oh, and by the way, the revision here was I forgot to put in the unit title in the middle here, so that was the only revision. So to start with unit 2A, I think question 1 is a good one to start us off, so let's begin there. Unit 2A and Unit 2B are really very similar units. Here, we're really just kind of getting started, thinking about unit analysis. So Unit 2B builds on the problems we're about to solve in this kind of way. It starts off by saying that we have a rectangular sandbox holding 18 cubic feet of dry sand. We want to know how much does the sand inside weigh, and then we'll have a related fact. This will be information provided on exam. 1 cubic feet of dry sand weighs about 100 pounds. So to start this one off, we can say we have 18 feet cubed of sand. Then the unit analysis will involve this right here. 1 cubic feet of dry sand weighs approximately 100 pounds, so we'll use that approximation. We then have to take this and multiply by a fraction. We want something that ends with a quantity of weight. So that means we should have pounds in the numerator. I'll abbreviate to LBS for pounds. And we're canceling cubic feet of sand in the denominator. So we take this part, 1 cubic foot of sand, put it down below. And this is the whole major idea of both units 2A and 2B at once. We know we're on the right track to just multiply by 100 if the units cancel out in this kind of way. Then multiplying this by 100 is just throwing in 2 zeros. We have 1,800 feet cubed. But don't forget, calculator is an excellent resource, a required resource for some of the problems. So no harm in double checking some of the numbers when you get through them. But that's one down, kind of a gentle problem to start out, and then we'll build from there. We'll do some harder ones as we go through our review. Any questions at all, folks, with the first one down?
Wouldn't it would be 1,800 pounds.
Oh, absolutely. Thanks for spotting that. So cubic feet, I should have canceled more carefully like that. And good eye, the remaining unit, it had to be weight altogether, should have been pounds. Let me put that in. LBS for pounds. Thanks for spotting that. That was a silly error there on the unit analysis, which was meant to be the major takeaway with problem number one. So, are there questions so far? Okay. Well, going from there, let's grab another problem. I'd say a lot of these are pretty similar, but this one's a little bit different. Let's take a look into problem three next. I don't know why, but the different font is really jarring. Let me try to get it back to the same. So we're told on this one, freelancer is paid $2,450 for a project that took 55 hours of work. Maybe it was building a fence, who knows, a deck, something like that. If we were thinking of how much this person made in a different unit, say hourly wage, we could get a better feel for, was this person cheated? Did they get a good value for their work? For example, if they're a lawyer, this is probably not quite right. So we'll see what their hourly wage is. We can start by saying, take the $2,450. We want the hourly wage. This would be in units of dollars per hour. But that's kind of the hint on this. Per hour tells us, well, the per part means divide. Let me get rid of that extraneous decimal point. We want to have this in dollars per hour, so take this, throw it below, 55 hours. And all we need to do is now just crank it out. So that's the logic on putting this one together. Again, a little bit different from this one where we're just multiplying by something. Here we thought about, like before, even though I missed that problem there, here, we're thinking about what should our answer look like. If it's hourly wage, we want units dollars per hour. And that's what we're picking up here with the dollars per the hour. Now we run it through the calculator. Take 2,450, divide by 55. And because it's money, we'll round this to the nearest cent. But keep in mind, that means if you multiply this to try to get back to 2,450, upon rounding, we're not going to get there. So this is just a way to see how the person was doing in dollars per hour, not to try to get the exact amount. So $44.55 is what we would get. Let me throw in the unit, $44.55 per hour. That's not too shabby. But again, if this was a lawyer, probably they're getting cheated on this somehow. Well, any questions, folks, on the second problem so far?
On the exam, are you going to ask us to round or are you going to accept exact answers?
I would accept an exact answer. And I'm going to be very verbatim with the way the instructions are written. So if they are written exactly like this, it didn't say anything to round, and you gave me a number that goes 44.54, looks like it's repeating, so a bar over the 54, that'd be a perfectly acceptable answer. Some of the instructions will indicate to round, and if you make extra assumptions like if it's money, it's appropriate to round, that'd be okay as well, depending on the context. But yeah, I'll try to be very specific on the exact rounding for each one of those exam questions. Other questions at the moment? Okay, let's try out one more problem and then maybe change the unit. And again, if you have any review document pulled up already, and there's a problem I'm skipping over that you would like to see solved, don't hesitate to ask about it. I'll be happy to change gears and definitely get into that problem. So I think the next interesting one might be problem number 9. We're combining some of the ideas we've used already, doing a little bit more unit analysis. And at this problem, we'll probably, let's see, this is something we want in cubic yards. So now we're probably going to use some table lookups, say the last page of the exam, to see what values we need. So here's the very next one. Let me see if I can paste that in a better way. There we go. So we have a new gravel driveway that's going to be 10 feet wide, 40 feet long. It's going to be filled to the depth of 6 inches with gravel. And so we have to know, when we call the truck to bring this in, how many cubic yards of gravel are going to be needed altogether. This is one of those problems where a diagram might not be a bad idea. So I'll write a really quick and fast diagram. Here's the 40 feet long for the driveway. For L, width is going to be 10 feet going this way. It has depth, but I'm not good at drawing this three-dimensionally, so I'll just come back to the depth as needed. And yeah, thanks for mentioning that. We'll definitely hit problem number 17. Let me just load it in the document for the next one to get to. So we will definitely do this one here, problem 17. I deleted 16, but once again, if there's a problem that seems we're skipping over, don't hesitate to ask. I'll be happy to look into it. So I'll just put it down here on the notes while we'll focus on this one. And don't hesitate to line them up in the chat either. Once I run out of problems, I'll look into the chat and get to the next problems as they come. So we have a length of 40 feet, a width of 10 feet. Let me just fix the penmanship there. The only thing I neglected was there's a fill depth of 6 feet with the gravel. So we're asking how many cubic yards of gravel are going to be needed. That's going to be a volume altogether. So that's going to be the length times the width times the height. So we already have these values indicated from the problem. We'll need the height, or you could call this D for depth. That might be a little bit more appropriate to the problem. Plugging that in there will get us started. So now we just about have a volume. It'll be the 40 feet times the 10 feet, the length and the width. And we're filling to a depth of 6 inches. You notice that that's already kind of annoying in a certain sense, because I can't just necessarily multiply these by 6. We'll break the unit analysis. It's the wrong unit altogether. So let's take this and work with it a little bit more carefully by converting that into feet, say. And Echo asks, is it going to be a paper test with space to work through for formulas, or a test on a computer? So what the Idaho Falls campus and also the Pocatello Testing Center will do is, I have a document that looks a little bit more like this. Imagine a lot less questions, but I'm formatting about like this between each question. Let me count that off so it looks a little bit more similar. Counting about 15 spaces between questions. The exam is going to look a little bit more like this. They'll print it out, so it's going to be on paper. So you'll just be filling out an exam that looks about like that altogether, with that page of notes on the very, very back. Yeah, you bet. Thanks for asking about that. Oh, there we go. So let's take this depth right here. It's 6 inches, but we know, say, we could do a table lookup. Hang on, I don't think that was in the table here. Or is it? Well, it's not in here so far. 1 foot is in meters. That's not super helpful. But I did look over this exam and proofread it. For an exam question like this, I would write into the question that use the fact that 12 inches equals 1 foot. Something we know for sure, but if it's a other random kind of unit, this information is written into the exam directly. So with 12 inches equals 1 foot, we can take a fill depth of 6 inches, multiply that by 1 foot. Let me fix my penmanship a little bit. 1 foot for the 12 inches. We'll get a cancellation here. Then 6 will go into 12 2 times, and that'll give us 1/2 of a foot, or 0.5 feet if you prefer. I'll go with the fraction, as depth is 1/2 of a foot altogether. This will give us a value in feet squared, and then we'll just have to make sure we hit the cubic yards part of the problem. So back to the calculator on this one. I have too many things open. There it is. We'll take 40 times 10 times 1/2 gives us 200 altogether. So we have 200 cubic feet. Yeah, absolutely. Let's throw in problem number 11 as the next one. I'll go in the order they're suggested. So it'll be kind of scrambled when we get through here. Maybe that's not a good idea to put that title in. So I'll do these problems in the order they come. Thanks for asking about that one. So we have a unit. We need 200 feet cubed for the gravel. But the next thing we need to do is now convert this into cubic feet. So again, I should have wrote that into this problem here to make it completely similar to the way the real exam is written. The real exam will mention information like this, as well as the other piece of information that 1 yard equals 3 feet. I mean, some of us have this completely memorized verbatim down pat, but exams tend to be slightly stressful. It's easy to just go blank on some of this information. So I'll have this provided into the problem if it's not one of those things that's conveyed as the very last formula sheet, say one of these tables. The major thing we need to do is cancel cubic feet. So we raise this side to power 3, this side to power 3. And so now we have the conversion factor that 1 cubic yard is 3 times 3 times 3, so 27 cubic feet. And finally, we come back over here, multiply by 1 cubic yard, divide by 27 feet cubed. That gives us the cancellation that were needed. And now we have the answer in cubic yards altogether. We're going to round this one to 2 decimal places. So this is going to be, now back in the calculator, 200 divided by 27. To 2 decimal places, that'll be a 7.41 cubic yards. So that's the rundown on problem number 9. It was a bit of a distraction because I'm intending to include this information. So we had to write it into the problem to get through it. But any questions at all, folks, running through problem number 9? Okay, another piece of advice, just to reiterate what we've been saying for how the exam is going to be graded. I'm going to be focusing on the numbers that you output. I'm going to try to grade on partial credit, but if you feel like you're just very fluent with this kind of problem and all you did is you went into the calculator and just got that answer, put it down, you won't be penalized for not showing the steps in the middle, but it's a good idea to show some detail. Because if there's a random number and I'm just not sure how you calculated it, for example, maybe you flipped one of the fractions, just something random, but you knew the overall process. If I can't connect to the dots on how you got to the number, you could lose all the partial credit on that problem. So show some details for what's about to go in the calculator, and that's a great protection. The other thing I mentioned is MyLab has this unfortunate feature where it doesn't emphasize the units as well as it really could. A lot of the units are just printed on the problem and you supply the number. So I'm not going to be critical on the unit you provided. I'm focusing on the numerical portion most of all. But if you track the units like we've been doing in class, this is just a way to logically know that you had to divide by 27 rather than multiply. And particularly when the units get a little bit more messy as well. But let's convert over to problem 17, then we'll jump into 11 next. Keep the suggestions coming and don't hesitate to throw out any kind of random concept question as well. Oh, this one is kind of fun. This one is from unit. Let me indicate where this one came from. This is from unit 2C. We have to use Pythagorean's theorem on this one. there was two Pythagorean theorem kind of problems, but if a question is going to be on the exam, it would be this one, not the really hard one where a ribbon is wrapped around a mailing tube or something like that. I felt like that one kind of went off the rails a little bit. So this says, imagine a steel railroad track that is exactly 1 mile. And again, this is what I'm going to put on the notes, that there's a conversion factor you need. 1 mile is 5,280 feet. So I'll visualize this distance. Let's go in feet, 5,280. So here's our railroad track, just as a rough sketch. We're told next, on a very hot day, the track expands by 2 feet. I don't know if that thermal expansion is completely realistic, but it might be. We have to ask the engineers on that. So this has gone 2 feet longer, but it's going to buckle. The track is anchored at the ends, so it's going to expand upwards. We're going to say into a shape of a triangle. It might be some weirder shape, but if we think in terms of a triangular shape, we'll be able to approximate how many feet the center will be away from the ground, because we're going to get a Pythagorean theorem in the problem. So in the center will be the height of that, the highest point of that triangle. So right here, here's the new shape. And now the new length is, again, 2 feet longer. So we had a length of 528 feet. The new length is going to be equal to 5280 plus 2. So 5282 feet altogether. But that's going to be the length going from here to here. And so what we want to put down next is the new length. Let's just take that thing and divide it by 2 altogether. If we divide it by 2, that will give us this distance going this way. So that's going to be 5282 feet divided by 2, giving us 5282 divided by 2, 2,641 feet. So 2641 feet. So that's this length going this way, 2641, 2641. And that was 5280 for the total feet. So here's the problem so far. And the question on this is, how many feet high would the center vary from the ground? Let's give that a color for the question. We're essentially being asked, how tall is this line segment when we put it down on the diagram? But the big observation is we now have a right triangle that we could work with to solve this one. Yeah, absolutely. Thanks for suggesting that one. Problem 27 we'll do after 11. This gives us a good list to go through. And I think I put 27 on my page of notes here as a good one to definitely look into as well. So I'm glad to see some overlap of the problems I selected as well. It's kind of cool. So now problem 27, or rather problem 17, the idea with this one is there's a 90-degree measurement here. And if we focus on just this segment of the triangle, we can calculate that height. It's messy, right? There's a lot of information that we've been putting down as we track through the problem. So the next thing we should do is just abstract away from our crude diagram of the track with it buckling upwards and focus on the thing highlighted in yellow. We're going to blow it up a little bit so we can just really see the relationships between these objects. Here's the height going this way. And the height here is the unknown. Let's give it a letter H for the height. We don't know that quantity yet, but we did come up with this side length going this way. That was the 2641. We found it by dividing by 2, and the same idea is going to give us this length going this way. That's the dead center, so divide this by 2, and we'll have this length. So back to the calculator. That's kind of fast. We can just throw in a 0 here. So 5280 halves gives us 2640. So now it's 2640 going this way. And here's a good shout out for another formula you might want to have ready to go. Pythagorean's theorem. Pythagorean's theorem says that in a right triangle, c squared, the most important side, the longest side, is equal to a squared plus b squared. So the critical use of Pythagoras' theorem we mentioned before is identifying which side of amongst the three is c. But c is always the longest side length that you see, the one that's opposite of where the 90-degree measurement is. This is the side length c in Pythagorean's theorem. And whichever one you call a and b is irrelevant at this point. You'll get the same algebra either way. So I'll think of this as a A, think of this as a B, and that's a great formula to be ready to go with. That's probably something that's going to come up later on in the course as well. It's one of those things that just seems to crop up here and there. So running through Pythagorean's theorem, in place of c squared, now let me actually write it down here so we can see the substitution better. In place of where we have c squared, we'll throw in, using our diagram as a guide, the 2641. Here, I'm going to leave off the units for now and just write it in as feet, as when we get to the end answer. It's going to be equal to a squared, so 2640 power 2, plus b squared. Inside here, we're just throwing in h. Really, you could drop the parentheses if you like and just call this 2641 squared, 2640 squared, plus h squared. But now we're kind of cinching the deal with this algebra. This is a big calculator operation, so take 2641 squared. That gives us 6,974,881. Equals, then let's do it again, 2640 squared. Change that one number. So 6,969,600. Plus that h squared. At this stage, we're just equation solving, trying to isolate the h variable. So we're going to subtract this quantity here from this side. Let's write it out just for the sake of visualizing it on the notes. Minus 6,969,600. Same operation here. Okay, we'll rebalance to a new equation with the square of the height that we want on one side. So let me write those out. You know, when you think about it, you can type in these numbers just as is, get the value. Let me just do that to emphasize what it looks like in the calculator. 6,974,881 minus 6,969,600. And hang on here. There's a problem, 7,4. That kind of emphasizes my point. It's tricky with all those digits. But if you left it in power 2, you could have just said 2641 squared minus 26. Let me try with the minus. There we go. 2640 squared. And I think I'm always going to be more accurate if I do it like this, subtracting it with power 2, rather than accidentally transposing a digit, getting it backwards, writing it out like that. But either way, we're going to get 5281. And by the way, if you have any questions on dealing with the calculator, that's a great review question as well to discuss. So don't hesitate if you are getting different values, if the calculator is misbehaving, I'll be happy to help out as we review. Finally, we're about there. The last thing to do is take the square root of both sides. So the square root of 5281 is going to be the height that the railroad track buckles upwards on the hot day. This looks pretty crazy. So we have square root 5281. It says this is going to buckle upwards. Let's see, to the nearest hundredth, 72.67 feet. That sounds like a catastrophe waiting to happen. So hopefully that doesn't ever happen. This problem is hopefully a slight exaggeration. 72.61 feet would be the height H under all of these conditions. Again, it probably wouldn't buckle as a perfect triangle like that, but if it did, that train is going to be launched and we'll probably have a huge disaster you'll see in the news. Well, any questions at all, folks, on finalizing problem 17? Okay, now we're off to next. Suggestion is problem number 11 on the list. So let's go grab that one. I think it deserves a brand new page. Problem number 11, we are in Unit 2B. And this is a kind of a random one. I'm glad this one was asked. There's going to be some random units, kind of like we see here on this problem on the real exam. And if I give you a random unit, I'll absolutely make sure it's defined like we see right here. We're told a horse is measured to be 16 hands tall at the shoulder. We want to know how tall is the horse in inches then? So we can start by saying, let's use the provided length. We have 16 hands. So that's a bona fide unit. It's defined to be 1 hand equals 4 inches. That means we can get through this one by multiplying by that as a conversion factor. We want to know the height in inches, so that means inches should be in the numerator when we write this out. And that directs us 4 inches should be up in the numerator to correspond to the 1 hand. So we cancel the units like this. We're going to get the overall unit in just inches to match with the problem. So now it boils down to 16 times 4. Giving us 64 inches altogether. So 16 hands works out to 64 inches. That's a random fact I would probably never know if not for this course. So that's kind of interesting in a way. Any questions at all, folks, on this problem's unit analysis? Okay, I know this is about the experience of the real exam. I mentioned it's 11 questions total, approximately 2 to 3 questions per unit, but some of them are just fast concept questions like these. Some of them can be a little bit more delved into step-by-step computations, drawing a diagram, like 17 and number 9, for example. But they're not all a big, long fist fight through the problem. Some of them are just kind of fast concepts like this one we got through. Let's see what we're getting into problem number 27 next. 27, I think that's the last one in the notes. Looks like we're talking about energy released by earthquakes. So if you're from California, this is a problem that probably is pretty interesting. I noticed visiting California, it seems like none of the doors shut right. Everything is kind of hard to shut because probably everything's been shaken a whole bunch. It's kind of interesting. Okay, there's a lot going on in this problem. The reminder is joules is just a unit of energy. And we're told the energy released by a magnitude 5 earthquake in terms of that unit joules is on the order of magnitude 10 power 12, approximately 2 times 10 power 12 joules, a gigantic amount of energy. Energy released by an 8.0 earthquake is on the order of magnitude 10 power 16 in joules. It says compare the energy of the magnitude 8 to the magnitude 5 earthquake. Express your answer in scientific notation to 1 decimal. Now, these questions are always kind of tricky and vague, just on the wording alone. What do we mean by comparing it? The thought is, we want to figure out how many times more energy do we get from the 8 magnitude earthquake versus the 5 magnitude. We can find that through a division. So that's the idea with this one, to try to divide. Oh, I hear you, Trinity. Instead of problem 11, example 11, I gotcha. So example 11, a population of 250 million, there's an average 500 deaths per year. What is the mortality rate per 100,000 people? Gotcha. I think you were referring to then sample exam version 1 is what we were looking into. Thanks for putting that in the chat. Let's grab that. And let's do that one after we do problem number 27. That's a pretty good one. I think there's a similar one somewhere as well in the version 2 exam. But here's example 11 from, I believe, sample exam version number 1. Okay, thanks for the clarification on that one. And we'll make that our very next question to get into after this one here. So this one turns into a kind of division problem. What we want to take is the thing with the larger energy. So we'll begin with the magnitude 8 earthquake. It releases the 6.3 times 10 power 16 joules. Abbreviation of that unit would be just an uppercase J. Divided by the smaller magnitude earthquake. Magnitude 5 isn't exactly small, that's scary on its own. But in terms of magnitude 8, it is very, very small. This one releases 2.0 times 10 to the power 12 joules of energy. So because we're doing this kind of comparison, joules will cancel out. Next thing we'll do is take the 6.3 divided by the 2.0. So we're breaking the problem down into the numerical part and then the 10 to a power part. I mean, that's numerical as well. So take 6.3, divide by 2.0 for a 3.15. We'll round this one in a minute, but let's start with the 3.15. It'll be multiplied by 10 to a specific power. Has anyone spot what exponent should go here? Yeah, good call. This one comes out to power 4. The exponent law in the background is a power of m divided by a power of n is a power m minus n. So really we're just taking power 16 minus the 12 to get the overall power 4. We're rounding this to 1 decimal place, so that will tell us that this comes out as a 3.2 times 10 power 4. It says to compare it. This is the comparison, but you know it needs some words to really tie this together. We can say a magnitude 8.0 releases 3.2 times 10 to the power 4 times as much energy than a magnitude. It was 5.0 earthquake. So that's a conclusion on that one there. Any questions at all, folks, on the run through with problems 27? Okay, let's get into the real question number 11 that was intended to be asked. I think this one is kind of tricky in a certain sense because we want to go for a specific kind of mortality rate, a standard that is great for comparing quantities on a national scale from, say, one country to a next, is the number of deaths per 100,000 people. I think this deserves a new page, so let's take this to the problem here, to the page here. First thing I would do to get started on this is just pull in this information. We have 250 million people, and there's an average of 500,000 deaths per year for those people. This one is then asking for the mortality rate per 100,000 people. So that's our overall question on this one. And this is possibly a good thing to say in the notes. When referring to mortality rate in this context, we mean number of deaths per, I'll just express as a fraction bar, 100,000 people. So this gives us a nice kind of yardstick so we can measure the quantity from one country to the next. To get to this kind of expression, we're just filling in the number in the numerator. And we have to start with the provided information. So wherever country this is, we have 500,000 deaths per year. So I'll start by saying 500 deaths, and let me fill out this unit a little bit better. This number of deaths per year specifically. Per year, per 100,000 people. So it's a complicated problem, really. This is a pretty big compound unit that we're putting all together. So 500,000 deaths per year. Then we'll divide by the population size, 250 million. So there's lots of different ways we could express this. We could write this as 250,000,000 if we prefer, or we could rewrite it in scientific notation. 250 million could be also expressed as 250 times 10 to the power of 6. But either way we do it, we're going to do about the same kind of computation in the denominator, in the calculator rather. So here's the 250 million people. And by the way, as far as the tables go, scientific notation works really well with the prefix, suffix, or prefix table that we see here. When, say, millions comes in, think in terms of mega or million, and it kind of just outputs the scientific notation you would need if you had to just write it down compactly this way. But going down this route, we're going to put this in the calculator just as we see it. 500,000 deaths, I'm going to just do the division right away. 500,000 divide by 250, 1, 2, 3, 4, 5, 6. Double check all those zeros, make sure they're right, and we get a 0.002. And this is going to be deaths per year per one person. Because I just took the entire denominator and divided all of it into that numerator, getting that value. But now we need to reach the goal of 100,000 people, which means I need 100,000 people in the denominator. But that's not too bad to fix at this stage. You could just go times 100,000 above and below. So if you did that, down the denominator, we have 100,000 people. That's just multiplying across denominators and then multiply across numerators. This is a decimal shift of 5 places to the right. But you know, just for the sake of accuracy, when there's lots of zeros getting involved, it's no harm in visualizing it this way. 0.002 times 100,000. Let me check the zeros on there. That'll give us 200 deaths. You could express the per year in this way if you like, just to abbreviate the unit. We have 200 deaths per year per 100,000 people in whatever country or population this would have been. So I think this is a good approach. Just put the information together, deaths per year, divide by the population size. Whatever the numbers are, you can just do a clean division. And then to get to the denominator we want, just multiply in this way, and that'll take us there. Let me highlight this just to connect the dots in the process. But does that make sense with this particular question? Okay, I think I ran out of questions, but don't worry, I definitely have more. So if you have another question you're thinking about, don't hesitate to ask about it. But looking into what we've done so far, let me think here. I don't know if we've done anything along the lines of, let's see, we did this one. Scientific notation we haven't done, but I think a big one we haven't really done is a percent problem. So I think probably a good one to do next might be either 21 or 22. Let me pull in problem number 22 for our next one to take a look into. So this one is about absolute change, relative change. Now that takes us to a nice formula that you might want to have on your notes as well. I think I have it somewhere here. There it is. Let's just pull this in. Okay, so pretending this is the notes you brought to the exam, here's a question that could come up. I mean, these questions won't come up verbatim, but the context will change, the numbers will change. And this was a pretty standard question for that unit on percents 3A. It says find both the absolute change and relative change as a percentage in the following cases. And here we're talking about the national debt of a country that increased from 2.1 trillion to 2.8 trillion over a decade. So to talk about the absolute change, the formula is we'll take the new value minus the reference value, but that's where it can get a little bit tricky on these. We have to subtract in the right direction, but there's often a time component. When it says from the 2.1 trillion, that's the reference value of the problem. When it says it went to 2.8 trillion over a decade, we're thinking of this as the present value or the new value, the value as it is now. So that would be our new value in the problem. So we can say 2.8, I'll keep the units as is, trillion, minus the 2.1 trillion. This is the reference value. This is going to come out as a positive number, but that would mean the national debt has grown for this particular country. And those units kind of got away from me. Let me put in that dollar sign so it doesn't look weird out of nowhere. So there's the dollar sign. We'll get a value of 0.7 trillion or 700 million if you prefer. But I'll keep it the way the numbers were expressed, just with a trillion unit. So that's our absolute change. Let me fix that real quick. There's a G in the word change. And now for the relative change. We take the absolute change in the numerator, so the same value we just calculated, 0.7 trillion, divided by the reference value in the problem. So notice that there's always this nice carryover following the color coding. If you had 2.1 trillion here, it goes back into the denominator for the same reference value. Now we just convert it into a percentage, go times 100, tack the percent symbol onto it. Units cancel. So we have just a pure percentage once we run it through the calculator. So we're taking 0.7 divided by 2.1, and as a percentage, go times 100. This will be 33.3%. So that finalizes the problem. We could say in words, if we wanted to, that the national debt has increased by 33% over a decade from its 2.1 trillion level. But if you leave it like this, you don't necessarily have to write in the context or interpretation. It's good to think about it just to make sure it makes sense. But that's the finalization for part A. It looks like part B is just a different scenario, but same kind of formula. Well, any questions with this one so far? Okay, we might as well do the part B now that's on paper. It'd be weird to leave it hanging. We're told here, the average number of daily customers at a coffee shop decreased from a value of 450 to 350 customers after a competitor opened nearby. Well, when it says it decreased from 450, it looks like the 450 was the reference value. When it said to 350, we mean they have 350 average daily customers currently. So this is the current value or the new value after maybe Starbucks opened up or something like that. Or maybe this is Starbucks and a local competitor came in and they're just taste better. So that could be what's going on. So if this is Starbucks losing customers, they're going to want to know about both the absolute change, but maybe more pertinent would be the relative change in that area. And then they'll make an informed decision if they have to close the store, like they've been seemingly doing quite a bit of. So we'll do absolute change. To start out, it'll be the new value, 315 customers, minus the reference value. It was 450 before the competitors moved in. So that's altogether a decrease of 65 customers. Then when we go to relative change, in our textbook, that we're going to consider the sign as important because it's going to give us the directionality. So we would go negative 65 customers divide by the reference value again, the thing that came second here. So even if I got this flipped, we might lose a point right here, but if you're consistent and divide by the second quantity, you wouldn't lose a point a second time. There's no double jeopardy on those kind of problems. I'll look at what you wrote on one line and see if you consistently brought this number down to the next. But if we got this one flipped and we flip the denominator again, we might lose points on both sides. The idea is to keep those two quantities consistent when we go into relative change. So put down 450 customers below times that 100%. So clean cancellation going this way like expected. Then back to the calculator, we pulled this up, feels like a 50 times already. Negative 65 divided by 450 times 100 to the nearest tenth, I think is what it was asking. Let me double check that. Yeah. We've lost 14.4%, or negative 14.4% decrease in customers once the competitors moved in. Well, that's the fast rundown with that percentage, relative and absolute change. Any questions at all, folks, on that example there? Okay, well, we're at the very end of the time. We've got about 6 minutes. So let's take a look into about what would look interesting for this last bit of time. Let's see. We did uses, abuses of percentages a little bit. You know, one thing we haven't done, which kind of fits with the amount of time we have left, is let's do a scientific notation problem to round out our review for today. We didn't get to solve every one of them. That would have been us talking super fast, probably wouldn't be productive. Answers are provided down below. And if you have any questions on any of these, maybe just specifically how to get to, say, the answer on this one, 200 deaths per 100,000 people, don't hesitate to ask. I'll be happy to provide in the solution to go along with the answer. But let's make this our last question for the day. It says, rewrite the following statements using a number in scientific notation. So here we probably would want to think, what exactly do we need for scientific notation? And this would be a good thing to throw into the notes as well, that you're allowed to bring to the exam. We probably all are pretty good at scientific notation after practicing, but again, it's good to have a reference for the sake of the exam, just to make sure we're on the right track. So we have two quantities we're going to write down in that notation. First to start, we have that the distance from Earth to the sun is approximately 93 million miles. So to get into scientific notation, the decimal point here has to travel all the way to the left until we get to a 9.3. So it can't be a 0.93 because we are not between 1 and 10. It can't be like a 93. That's an easy mistake to make. I think I made it a couple of times in the notes. It's got to be directly a 9.3 to qualify for this part of the instruction. Then it gets multiplied by 10 to some power. Anyone spot what the exponent should be for this one?
Six?
Let me see. We go 1, 2, 3, 4, 5, 6. 6 would land us at that spot between the 3 and the 0. So that'd be really close. It looks like we have to go one more to a power 7 on this one. So this one should be at 10 to a power 7 altogether. And again, these are kind of interesting problems because we have the opportunity to double check them as well. On a calculator like say this one, if I go 9.3 times 10 power 7, what it looks like on the calculator, it's hard to see on the Zoom, it looks like this. 9.3, my time symbol looks like this. 10, then my power button would be here, kind of up and to the left of the 7. It's a symbol that goes up arrow for exponent. Throw in the 7 and hit enter, and it outputs 930000000. A shame it doesn't throw in commas for that. But then we could double check it's the right quantity. So these are kind of nice problems where a calculator like this one is a pretty fast double check. And that's great because sometimes there are so many zeros, these are hard to really count off. So let's try this out again on this problem. It's got to be a 6.7 times 10 to some power. So let me see, let's pretend this is a real exam and the red dot is like my finger. 1, 2, 3, 4, 5, 6, 7. That's an odd coincidence. Sorry about that. So if I go 7 spaces, what should we put here as the actual exponent? Anyone see what it should be? Yeah, good call, Amy. This one will come in as a -7 altogether. And again, you should be able to throw this into the calculator as a double check. It'd be 6.7 times symbol, 7 to power, and the negative sign would have to be this one on the very, very bottom. You can't use the minus symbol. You'll type in, let me see what it looks like on this calculator, 6.7 times 10 power. It looks like kind of a small dash like that. Put in a 7, and you get 0 point, let's see, 1, 2, 3, 4, 5, 6. 6, 7 is what this calculator model would output. Well, that kind of rounds out the amount of time we have so far, but any questions at the moment, folks, with anything we've done so far today, or just generic questions about the exam? Okay, well, thanks for the participation on this and the great problem suggestions. I had a list of problems I want to take a look into, and there was pretty strong overlap with what folks suggested in class today, so I thought that was pretty neat. With these entire page of notes that we did, I'm going to post them on the Canvas page between the Unit 3B and the Quiz 3, so it's available. And once again, if you haven't scheduled your exam, and maybe if you have any questions about the instructions on doing so, don't hesitate to reach out. When you're working homework over the weekend, don't hesitate to reach out as well. I'm going to be checking my email every morning, and I'll be happy to get back with you and help out. But have a great weekend, folks. We won't have class on Monday because some people might potentially be taking an exam during the class time. We'll be back to class on Wednesday after getting through the exam. But have a great night. Have a great weekend. I'll see you all next week.
Thank you.
You bet. Have a good one.